Hi. So what we're going to do today is talk about random matrices and how they are connected to free random variables. So I call them free random matrices, but this is a slang. And we'll talk a little bit about interlacing polynomials. And the goal of this is not a standard tutorial. It's to help understand the works of MSS that Gil is talking about in the last two lectures. So help understand this material and where this comes from, and also prepare some of you to or all of us who listen to the end of semester projects some of them are related to random matrices. So I'll start with some motivation and then connect it to the course. So assume we have two symmetric matrices A and B, and we know their spectrum. So we have the spectrum of A. We will denote by alpha 1 up to alpha n. Let's say n is capital N is the dimension of the matrices. And this is set with the multiplicities, the eigenvalues of A. And assume we have similarly the spectrum of B. And what we're interested in many applications is to know the spectrum of A plus B. This is a general goal, which, I mean, there are many cases, but I always tend to think about graphs. What happens if I sum the adjacency matrices of two graphs? What would be the resulting spectrum of the graph? And what can we say about the sum of two matrices, about the spectrum? It's not nothing, right? You know something, right? If I write this spectrum, let's say as lambda 1 up to lambda n, what can you say about any of them? You know something. You know that, for example, lambda 1 is no more than alpha 1 plus beta 1, right? This is right. If you think about eigenvalues as Rayleigh quotients, so you can write lambda 1 equals the max. I didn't prepare this, but I'll try. The max vector x such that the max vector x of the expression x transpose A plus B x over the norm of x. And if you open this up, you can see that this cannot be any more than these two separate expressions. So you know something. You can also analyze the trace, right? And you know that because, and I'm saying it because I'll use it later, but you know that the trace is the sum of the eigenvalues, and trace is summable. So you know that the sum of the lambdas is the sum of all of these. But apart from that, you don't know much. And you have some hope to analyze it, but for the general case, you don't know anything better. And we want to connect this to free probability. In order to do so, we need to define random variables. And the random variables we are going to define are denoted by, here I'll denote it A and UB. These would be the distributions of a random variable. So let's think distributions. So mu A would be just I'll put similar weight on every eigenvalue of the matrix. So it would look like 1 over n times delta alpha 1 plus delta of alpha 2 plus delta of alpha n. I'll show an example in case it is not clear. No, this is a fixed matrix. This is a fixed matrix, but given a fixed matrix, I can think sometimes it's called the, I forgot the term, the empiric distribution of the matrix. What's empiric about it? That the matrix is not random, but you sort of pick an eigenvalue uniformly at random. So just as an example, if alpha 1 equals 2 and alpha 2 equals 0 and alpha 3 equals alpha 4 equals alpha 5 minus 1, then in this case, I can draw the distribution. I have minus 1 over here and here. I need to draw, so this is with multiplicity 3, so I need to draw the lines 0.2 and 0.6. And the distribution would look like this. I have minus 1 with probability 0.6 and 0 with probability 0.2 and 2 with probability 0.2. Okay, this is the distribution associated with the matrix, or the empiric distribution of eigenvalues of A. And the B is similarly written. So and what I care about now is to analyze the distribution of new matrix of the sum. As I said, in general, there's no hope in doing so because the spectrum hides all the structure of the eigenvector. So there's nothing you can really do apart from the trivial things that I've done. So in order to have any hope, we need to introduce some randomness into the process, and the way we do that is by replacing B with I keep B, but I replace it with B multiplied by a hard random matrix. So here Q is distributed according to the R measure over the orthogonal set matrices of dimension n. Orthogonal, I mean real unit. And Gil described this distribution in class. So, and what's important about this this measure over matrices is that it doesn't change the spectrum of B. So after this operation, the spectrum remains the same. The set of eigenvectors, it remains a set of n orthonormal eigenvectors, but they are completely random. And here we can have some hope in analyzing this sum. So here, instead of the spectrum of A plus B, I'll write spectrum of A plus QB. Okay, and I ask what is the spectrum of this new random matrix? Yes, okay. Now, I want to correlate this to free probability, and I will do so. And I must say, we've done the whole course in order to reach a point where we have a random variable two random variables A and B, such that they have analytic distributions in the analytic sense A and B are elements in an algebra A, where I have a non-commutative probability space A and P. So these are two, let's say, self-adjoint elements with analytic distributions UA and UB. And we worked hard the entire course to reach a point where we can say that if A and B are free, then I can write the distribution of their sum as the convolution, the original distributions, if I assume they are free, or I can, we have seen as an exercise that I can say that instead of looking at u a plus b, I can look at u a plus ub u star, where u is a hard unitary that is free of them. Yeah, I'm not writing. I won't write it down. And I want to do something similar here. So I want to say, I wish to say phrase like the analytic distribution of the random matrix mu a plus qbq star. So in this, I want to be in some sense free from that one. I want it to equal u of a additively convoluted with mu of a. Okay, this is the sort of thing I want to be able to do. And why do I care about it? Well, if it wasn't the case that real elements like matrices have this kind of behavior, I in particular won't get into this field of real probability, right? Because if it was just some abstraction that it was amazing by its own, we've seen that there's like another type of independence, and it's the only other type, and it's a whole bunch of really beautiful mathematics, but it's not, if it doesn't apply to real world object, it doesn't really help us in applications in computer science, for example. And matrices are the real objects that I want to analyze. So I want something like this to hold. But does it hold? I mean, is there any problem with what I've written here? There are two that I count. Do you have any?
I think you mentioned it. So in order to write the physical written, you need to have like variables and some other algebra, and you have to define. I mean, it's not even defined, I guess.
I mean, this is a distribution and this is a distribution, so this operation is well defined. So, but okay, so I'll say two issues with the statement here. One issue, maybe I'll do this in red. One issue is that this has to be a discrete measure, right? In the definition above of the measure of a matrix, it has like these atoms, and we've seen that even for the simplest distributions, the convolution is typically not discrete, continuous. This is an informal discussion, right?
Why is the left one straight?
We have a fixed dimension.
But A plus Q B Q star is not a fixed matrix, right?
Right. So now there's the second part that it's not even well defined what I wrote here. As when I say this equality, I ask like for which instances of Q. I expect something to happen for a random Q, but if Q is random, what does this measure even mean? Is this the average? And if so, the average over. So how do we even find what is U of A plus UB? Not even well defined. Okay, so but in real life, when we draw random matrices, let's say we draw something that resembles a hard unitary, and we do this summation and we look with our bare eyes on the distribution of the eigenvalues, it does look like this. Okay, so it will be discrete. So if this distribution looks something like this, and we look at the histogram of these matrices, we will likely see something that resembles it, like the proportions here are not of 0.2, 0.6. We'll see something that resembles it, and this is not a formal proof. This is just like observation. So we expect something like this to happen, and we need to formalize it. And in order to formalize it, we have two options. And these are distinct options that, at least for now, don't go well together. And the two options are to go in the route of either asymptotic freeness, which I need to formalize, and the other part is called finite free probability. And this is the route that Gil is lecturing about in the last two lectures, and this is the initiated by the works of Marcus Pillman and Srivastava. Okay, this was initiated by their work, and these two regimes are sort of separate from one another. And this will be covered in the, I hope, in the final projects in the seminar of the course. These are chapters 22 and 23 in the book. And I'll say a little bit about it first before I talk about the MSS work and the finite probability. Okay. So I cannot write this expression just take it like this, even though it looks like it in observations. I need to formalize what I mean here. So let's formalize what is asymptotic freeness and what do we want from it. And as you guessed, the asymptotics here are going to be as the dimension goes to infinity. Okay, so now I need to have a sequence of matrices A1, A2, and so on. Sequence of matrices B2, B1, B2, and so on, such that the distribution of the eigenvalues of AI approaches some distribution. And notice, all these are discrete measures. This may be discrete, but may also not be. Okay? And this is as I goes to infinity. And I assume they are growing in size. Otherwise, it's not very interesting. And same for the B's. And what I want to say here is that I want to treat the I want to now treat this eigenvalue distribution of their sum as a random variable for each choice. These are of the same dimensions, and for each dimension, I'm going to draw a hard unitary at random. And what I want to say is that mu of AI plus, I write QI to make sure that the dimension goes in here as well, VI QI transpose approaches the approaches mu A convoluted with mu B, and this I want to be in distribution as I goes to infinity in distribution. What do I mean by this? I want to say that we've talked before about convergence in distribution. I want to say that every moment of this distribution, if I look at the kth moment, of this distribution, I want to say that I fix a number k, I look at the kth moment, and then I take the dimension to infinity, and I expect it to equal the kth moment of this distribution on the reference. Now, this is a very strong statement, and I hope we'll prove it in the seminar part. It is, at least for now, somewhat problematic for our use cases. Because what we want to prove eventually in our applications, at least, okay, depends what the application is, but for graphs, we mostly care about lambda 1 or lambda 2. I want to say I want to bound the support of the spectrum. And the statement about convergence in distribution, even though for some applications it's really strong, doesn't give me that, because I can be really close in many of the moments to what I want to be close to. But it can be the case that if the support of this is pretty small, then this has, let's say, an atom of very, very far to the right, and I cannot, and especially for any finite dimension, I'm not able to say almost anything. So even if I prove, so convergence in distribution tells me something about moments. So if I say that the kth moment of, say, this distribution equals the kth moment of that one, let's say plus O of 1 over the dimension, even if I know a statement like this, it doesn't tell me, which is what I expect from asymptotic, from the convergence in distribution. I'm still not able to say even for this particular n, how far is the support size of this from the support size. Okay, so for some applications, this is not.
I still don't understand the notation like UAI plus QIVI.
Right.
Didn't define it.
Right. So now that's true. So now as the matrices are not constant, but rather random variables themselves, I need to have another look at the distribution UA. So, for example, if let's say C is a random matrix, so now what I need to define that this is each of these is defined as it is still for any choice of C, it is still discrete, but now these are random variables themselves. So this is like the first eigenvalue of the matrix C, and this would be the second eigenvalue of matrix C, and so on.
Looks like a measurement. Oh.
Right, but I do not. Yes, right. And what I say here, yeah, I tried to glance through it, and I didn't prepare all the definitions because I wanted to talk about finite freeness. Yeah, okay. I'll leave it for the seminar part. But there's a way to properly define it such as this. Yeah, I'm still. I didn't write this properly now. Okay, so for finite freeness, the approach is a little different. So in the finite case, I want to recall what we started with when talking about it, and recall that in the proof, I mean, this was a definition. We said that we first proved that this notion is well defined, but we didn't say how to calculate it. In order to calculate it, recall that we had that from each random variable A and B, we take the R transforms to be, say, RA of Z and RB of Z. And we knew that the R transform of their sum, meaning the R transform of the distribution A plus B, and Z equals the R transform A plus the R transform. This was proved using the cumulants relation of free random variables. And in finite freeness, we look directly at matrices and we think, going back here, about how these eigenvalues can be encoded rather than these distributions. And the other way to encode all the eigenvalues is the characteristic polynomial. So if we look at the characteristic polynomial of A, you know that it equals the product x minus, this is the notation of the characteristic polynomial of A with variable name x. It's x minus alpha I for all the i's from 1 to n. And so the same information is encoded here and here, it's just a different way to look at it. And we can denote this as a PA and similarly PA of x, and we can similarly write PB of x as the characteristic polynomial of B. And we define the solution of polynomials. So we look at PA of x, look at PB of x as, well, I want to say, and this will be well defined now, I want to say that this is the characteristic polynomial of A plus B, but we said that in order to achieve freeness, we need to introduce some randomness. So it's the multiplication of B with a hard unitary Q, but in this instance, I need to take the expectation for the hard measure Q. And this is a very in first glance, if you know free probability, this is a little weird because what I take the expectation here, these are polynomials. For each fixed q, this is a polynomial. And when I take the expectation, I take the expectation coefficient by coefficient. Even though the objects I care about are the eigenvalues and not the coefficients. But this is the definition of the convolution of the characteristic polynomials, which, as was proven in class by Gil, it does not depend on A and B really. So I can take any two matrices with these characteristic polynomials, and the Q's, the random R unitary sort of strips away all their structure. So this is the definition of the convolution. However, the definitions of the Cauchy transform and the R transform are similarly to what they were before. So the Cauchy transform is, you can write it as 1 over n, the sum of x minus alpha I. This is of the Cauchy transform of the matrix A. But this is the exact same as the Cauchy transform of mu A as we defined before. Okay, this is a variable. And similarly, we have the K and the R transforms. And what is surprising when proving things directly about the polynomials is that a similar relation holds with an inequality. So if I have these two matrices A and B as we had, and I want to analyze something about their sum, then I do know that so this is the free case, and in the finite free, I get that the R transform of the matrices A, let's say the R transform of the convolution PA of x convoluted with B of x is bounded by the sum of the R transforms. R A of x and x. And for z. Yes, it's like the equality of the cubes. Right, there's no polynomials here, it's just distributions. Here I proved something about polynomials, about R transforms of polynomials. And what's surprising here, if you compare it to the asymptotic freeness, is that this holds for every dimension with an inequality. And now you may ask whether inequality helps you. Okay, there are two questions to be asked here. One is whether an inequality is even helpful. Two, if you're, I don't know, sort of, don't have the right word. Maybe equality holds, but you were just not able to prove it for any dimension. But I have to say that, and you will show it in the lecture, this is not the case. The inequality here is real, and it is smaller the dimension, the stricter the inequality is. And you may think about the free part, the free random variables as the limit of the R transforms as the dimension goes to infinity, but you need to define it properly. In small dimensions, the inequality here is the real thing. And the first question comes to mind of whether this helps us, because in the case that there was inequality, we were able to actually calculate the probability distributions of the sums. And here we're not, because we only have a bound. It turns out that for the sole purpose of not, now, I won't be able to necessarily calculate this polynomial over here by this theorem. This inequality here is enough to bound itself. Okay, and this is crucial for some applications. So it depends what exactly you want to achieve, but this inequality is in many cases enough for just bounding what lambda 1 is.
We have a bound one day.
Right. So you are able to use that to achieve a bound on both directions of the support. However, if you want to say something about a particular Q, you don't necessarily can simultaneously bound the support. This is the last chapter of the course, but you won't necessarily be able to bound both sides of the support for a particular choice of Q. Okay, this is a little bit trickier. But for the expectation, you are able to bound both sides. Okay, I have something more to do, but it will take more than 10 minutes. I'll just do it asynchronously. So I hope that this gave you some sense of what's happening and also gave you motivation to pick this as a final project. I hope the most one of you will take. And that's it.